classical information theory, and we introduce the formula which is called Shannon entropy. Shannon entropy, and in order to get this formula, we can get this formula in two different ways. First of all, we can consider just now some messages and try to understand how many information contains a received message. There is some another way to get Shannon entropy. It is axiomatic way. So we can give some axioms concerning entropy or amount of information, and then using these axioms we can get formula for with which we can calculate, we can measure the amount of classical information. So, but let us consider the first way to get this formula. So let us consider some very simple example. Suppose that we received some message, повідомлення, and let us this message contains only two letters, A and B. And this message, it is set of these symbols. It can be AB, or it can be, instead of AB, it can be 0, 1. It can be 0, 1, which corresponds to classical bit. So, for instance, let us first message. We have the following. We have the following message: A, and so on. A, and so on. And we have a question. We have the following question: how many information contains this message? How many information we can get, we can obtain from this message? What do you think about the amount of information in this message? Прошу?
1 біт.
Ну, можна і встановити, що це є 1 біт, хоча насправді це є 0 інформації. Ну, нічого не можемо сказати. Абсолютно нічого. Тобто прийнято, що ось такі повідомлення, intuitively we understand that from this information we cannot get information. So this message contains no information. So we suppose that this information contains no information. It is uniform set of message. We have absolutely the same letters. We don't understand what it means. Nothing. So it is zero information. It is zero information. Amount of information is zero in this case. So intuitively we understand that this message contains no information. Let us consider second message. Second message. Second message. Suppose we have A, B, B, A, B, A, so on. So here we understand that in this message can be we can find some information. So in this message can be coded some amount of information. So similarly as in the first case, we understand that first case contains no information, but here we understand that here we have some amount of information. And now there is problem how to calculate, how to define the amount of information, of this information. So in order to get or to find the amount of information and to define the amount of information for such messages, let us consider the following. We have P1. It is probability to find in this message A. It is probability to find A, and P2, it is probability to find B. To find B in this message. Of course, because it is probability and we have only two possibilities, A and B in this message, so of course P1 plus P2 is equal to 1. So and let us, this message contains n symbols, and let us n is sufficiently large number. We have very large number, n is very large number, and then when n is very large, we can calculate how many in this message we have symbol A and how many B. So P1 multiplied by n, it is number of symbol which we can find in this message, symbol A. And similarly, P2 multiplied by n, it is NB, number of symbols B, B, symbols B. So we have very simple situation. We have a symbol in which with probability P1 we can find A, with probability P2 we can find B. And then when we have sufficiently large n, then number of A is this one and number of B is this. So, and now let us try to calculate the number of different messages in this case. How many different messages we can write in this case. Як багато різних повідомлень ми можемо написати в цьому випадку, якщо є n A символів А і n B символів B. So we have a question, how many messages we can obtain in this case. So we can easily calculate, let me write this formula, number of messages, different messages will be n capital factorial divided on P1 on, let me first of all write in such a way, factorial n B factorial, it is n factorial divided by P1 n factorial P2 n factorial. Let me explain this on a simple example. Suppose we have such only message A and B. So we have two possible messages, AB and BA. Suppose we have A, B, A. So here we have such message. We can also have possibility to get such message, maybe such message, and so only three possibilities. So when we have many A and many B, number of different messages can be calculated with this formula. And now let us consider that n is sufficiently large, very large number. Then for n factorial, let us use the Stirling approximation. I think that from probability theory, you have a course probability. You remember this formula. It is this is not very important, this number, but let me write square root from this 2 pi and exponent here, n divided by exponent in number in power n. It is approximation for factorial for large, very large n. So, but because we considered very large number n, instead of factorial, in limit n to infinity, we can use Stirling approximation, or Stirling formula. So, consider the next, continue this calculation. It is 3. So now let us put instead of factorial this Stirling approximation here, and for number of different messages, number of different messages in this case, we get the following formula. It will be 1 divided by, but okay, let us write n factorial. It will be n in power n, because all these constants cancel it. So here we will have n in power, let me write in more accurate way, n in power n. Instead of this term here and here, we have p1 n in power p1 n, and here p2 n in power p2 n. So we get the following, the next. Here we have n in power n, here p1 in power p1 n, multiplied n in power p1 n, and here p2 n, and n in power p2 n. We can combine these two multipliers. So, and together we get that it is p1 plus p2, but it is 1. So for this term and this one is cancelled. So this and this is cancelled. So we can continue. 1 divided p1 in power p1 n multiplied by p2 in power p2 n, and so it will be, we can rewrite it as p1 in power minus p1 n, p2 in power P2n, or it can be written in this form, 2 in power logarithm from this and this one, so it will be minus so what we get n p1 log with basis 2 p1 and minus n p2 log with basis 2 p2. Or if we can write 2 in power minus n, and here we have p1 log in power p1 minus p2 in power log 2 p2. And finally, let us write it in this way. It is 2 minus n multiplied by s, where we introduce notation s is equal to p1 log 2 minus, sorry, here write plus and here minus. P1 minus P2 log 2 P2. So number of different messages can be written in this form. It is 2 in power n multiplied by s, and s it is called just Shannon entropy for one symbol. It can be called as Shannon entropy for message which contains n different symbols. But when we divide this over n, we get that it is n s, and this s is called Shannon entropy for one symbol. Shannon entropy in this message which contains one symbol. And Shannon entropy can be considered as a value of information which we can get from this message. So it is number of different messages in this case, and this power is called Shannon entropy. It is Shannon entropy for message which contains n different symbols, or in different way written, and this entropy divided by n, it is Shannon entropy for one symbol. So in fact, we get a very important formula which can be considered as a number, as a value of information which we can get from this message. So in this message we can code, this message can code some information, and number of these different messages is related with amount of information which can be written in this message. So Shannon entropy, it is just formula which is definition of Shannon entropy. Shannon entropy. So maybe you have question concerning Shannon entropy. So number of information, or value of information which we can read in a given message with in which we have A with probability P1, B with probability 2, is related with number of different messages which we can write in this case. So it is number of different messages. And this power is called entropy, Shannon entropy. So maybe you have a question concerning this definition, because in fact it is a very important formula which we will use in our next calculation. And we consider properties of this formula, properties of Shannon entropy, and so on. So before considering the next properties, maybe you have a question concerning definition of Shannon entropy. І вправо, і вверх, отак, добре. Так, цей Zoom якось простіше, тому що цей Teams, він на екрані, на комп'ютері, він показує все в другий бік. Тут сунеш сюди, воно сунеться в другий бік. Дуже незручно. В Zoom було простіше з того. Це якийсь капець. Тут це можливо. Так, Shannon entropy. Так що, для того, щоб ввести поняття чи кількість інформації, ми зробили наступне. Давайте я ще раз. Це є важливий момент. Ми розглянули повідомлення символів великі, яке містить велику кількість символів, але тут є тільки два символи А, Б, з ймовірністю P1, А, з ймовірністю P2, Б. Ну, тоді для великих n середня кількість А це буде P1n, а кількість B буде P2n. Тоді ми можемо порахувати, скільки повідомлень ми можемо скомбінувати з цих кількості А і Б, різних. Ну, дуже просто. n факторіал – це скільки всіх можливих перестановок. n-а факторіал – це кількість перестановок в рамках одної букви А. Ясно, як ми ось цю букву, наприклад, в повідомленні і цю переставимо, нічого, меседж не зміниться. Так? Якщо ми Б переставимо, чи ці Б, також нічого не зміниться. А скільки є різних перестановок в рамках одної букви? n-а факторіал і n-б факторіал. Тому кількість всіх повідомлень різних є ось така. Кількість всіх перестановок всіх букв поділити на кількість перестановок всередині тої самої букви. Ну, тут видно, що тут кількість повідомлень, як приклад писав. Потім формулу Стірлінга використаємо для великих n. n факторіал пропорційний до n в степені n, якщо n великий. Ну і далі простенькі обчислення. Кількість повідомлень, а що то я написав? n message. Кількість повідомлень. Так, я перепрошую, невеличка перерва. Зараз, секунду. Sorry. Так, чи є у вас питання до цього? Ну, давайте його нема. Тобто ми порахували, скільки є різних повідомлень. В цьому випадку це є 2, ось в цьому степені n помножити на s. n на s – це є ентропія цього повідомлення, скільки є інформації може бути в цьому повідомленні. Так що кількість інформації, яка означається в цьому повідомленні, яку ми порахували, чи ось так означили, це є n помножити на цю букву S, S маленьке, чи S просто без індекса. І S – це є ентропія, чи кількість інформації, яка міститься в одному символі, яка припадає на один символ в цьому повідомленні. А на все повідомлення припадає оце S помножити на n. N на S – це вся кількість інформації, amount of information in this message. So, and finally, at the end of this lecture, let us consider let us consider more general case of message, and let us have a message which contains symbol A1, A2, and so on, with A, let us n, an, with probability P1, P2, and so on. Sorry, with probability P1, P2, Pn. So, and this result can be easily generalized for this case. So, in this case, number of messages of different messages, it will be n factorial divided by P1, and it is number of symbol A1 in this message factorial, P2 n factorial, and so on, Pn, small n, capital N factorial. And absolutely in the same way as we get formula for Shannon entropy in the case when we have in message only 2 letters, we can give similar result in this case. So here we get that it will be absolutely the same result, exponent n multiplied by s, but here s, it is minus sum over a from 1 to n p I log in basis 2 pi. It is Shannon entropy in this general case. You remember the entropy in thermodynamical case. So let me write this entropy. We can compare this entropy. It is minus Boltzmann constant, temperature, sum over probabilities, pi log only natural log, but here pi, it is probability that physical system is in some state I, and T is temperature, constant, Boltzmann constant. So an entropy in thermodynamical case is defined in this way. You can find that it's very, very similar formula, but in information theory, here it is written a log in basis 2, and in thermodynamical case here we write natural log. But in fact, it is very, very similar formula. And here also we have dimension constant, which is just related with energy. K multiplied by temperature give dimension energy. And in information theory, entropy is dimensionless value. And difference only here. Here we have, in information theory, we have log with basis 2. Why just we considered such log? I will explain in the next lecture, but now we can finish it, this lecture, and maybe you have some question.
Питань нема, але скоріш там перед останнім, після останнього дорівнює двійка має бути степень, а не експонента. Якщо я правильно розумію.
Yes, of course, yes. Thank you very much. In power 2. 2 in power ns, yes. Maybe comments, once more comments. Добре, то якщо нема більше питань, таким чином, today we introduce very important formula, namely we introduce Shannon entropy. Shannon entropy written here. And Shannon entropy, it is measure of information in message. It is number or it is value of information in a message. So you can verify that when we consider only message A, and so on, we can calculate number of information using this formula. So entropy in this case, so then what it means? It means that probability of A, it is 1, P1, and probability of 2, and so another maybe symbols is 0. So using this formula, what we get? We get minus 1 log is basis to 1, minus 0 log 0, it is 0. But it is also 0 because log 2 from 1 it is 0. So we have 0. We can calculate amount of information in this message, and we get using Shannon entropy. We get that Shannon entropy in this case is 0. It just corresponds to our intuition. When we consider this message, we understand that amount of information is 0 in this case, and this Shannon entropy just gives this result. Okay, with this we can end our lecture, so time is over. Таким чином закінчуємо на цьому, час вийшов. Якщо ще у вас є якісь питання, то будь ласка. Я вам дам, в мене є такі накидки лекцій по цьому курсу, англійською написані. Правда, він не вичитано і не виправлено. Минулий раз там, може, я трошки виправлю ті помилки, які я познаходив, і тоді вам зможу скинути. Це буде література, і там же буде також література на інші посилання, де ви можете все це знайти. Так що наступний раз я вам постараюся скинути цей текст лекцій, а також в тому тексті лекції буде та література. Прошу. Добре, ну то ніби все на сьогодні. Ми з вами коли бачимося? У нас є лабораторні чи практичні, це називається. Коли у вас ці практичні є?
Середу.
Давайте собі напишу. Середа. Яка пара у вас? Не пам'ятаєте?
Третє.
Третя пара. То ми наживо бачимося, ви приходите в середу, так?
Так.
Добре. Наживо. Добре, то тут Драгоманова 12. Якась там аудиторія буде. Там, певно, написано якась є. Може буде вільна 10, нам би було краще в 10, ніж там десь. Краща дошка. Добре, якщо нема більше запитань, тоді бачимося в середу з половиною групи, а половина інша наступна.
До побачення.
Все, до побачення.